Okay, it's 2:30, so let's get started. Last time, I talked about this problem called flow, right? So what is this problem, right? I give you a graph, and I give you two nodes, S and T. And what we're trying to do is we're trying to send as much flow from S to T while respecting certain constraints, right? The constraint is like, on any edge, the flow cannot be bigger than this number, right? The capacity of the edge. Sorry, last time I may have said cost kind of interchangeably, but this is the maximum amount of flow that can go on this edge, okay? And the question is like, how much stuff can I send from S to T while respecting that constraint? Like, the stuff on every edge cannot be bigger than the capacity of the edge. And also, like, for every, inside, node here, whatever comes in has to be the same amount that goes out, okay? And the question is, what is the most amount of stuff I can send from S to T, okay? That's the flow problem. That's called a max flow. And right, like we introduced this thing called the min SD cut, which is, it's a way to separate S and T, and we measure like the sort of value of this cut by how many edges go from one side to the other, the sum of these capacities. And that's like, a min SD cut is like the best way to separate S and T, right? It's like the cut with the smallest amount of stuff that you can send through, okay? But that also turned out to be something called max flow, right? These things turned out to be the same. And like I said, a flow is, you want to send some stuff from S to T while respecting those constraints. And the nice thing was that max flow is equal to min SD cut. So that's like a fundamental theorem. Pretty cool, pretty surprising. And the way we proved it was by giving, by considering this Fulkerson algorithm, right? What it did was say, okay, how can I greedily send more and more stuff from S to T? So what do I do, right? Say as long as I can find a path from S to T where I can send more stuff, I just keep doing it. And then I keep doing it until like S and T become separated in this graph G sub f. But as long as there is a path connecting S to T, that implied like a one more channel kind of to send stuff in, okay? All right, and the running time was O of m times f if I'm promised that all the capacities on the edges were like integer numbers, right? Like 1, 2, 3, 0, and so on. Yeah, so the running time was m times f, where f was the value of the maximum flow, okay? All right, so any questions about what happened last time? At a high level, how Fulkerson worked, why it works intuitively, running time. Okay, so now for this class, we're going to see like, I told you flow is a very powerful algorithmic primitive. We're going to see lots of cool applications of flow. But first, one kind of statement that like seems not so useful, but is actually really important for some of these applications is the following, which is, right, if I give you a graph where all the capacities are integer numbers, then there is always a max flow where every flow on every edge is an integer, okay? Why is that? Like, how does the Fulkerson algorithm work? It only sends integer stuff, right? Right? Like, what it does is finds an augmenting path, and it says what is the smallest capacity on the path, and it sends that. So this is not clear like before the fact, right? Like it could be that like it could be some rational numbers floating around that says the flow. But it turns out if I promise that all the capacities are integers, the flow will also have the property that on every edge it's an integer, okay? And that's a non-trivial property, as we'll see shortly, okay? That will actually give us a way to like solve lots of cool problems just because we know it has to be integer, okay? Any questions? Does that statement make sense? Why, like, if the capacitor are integers, the flow would also be integer. The max flow, there is some max flow. There actually can be a max flow where, like, the values are not integers, it turns out. But there will always be some max flow where the values are integers, and that is a proof by how the Fulkerson algorithm works, because it never initializes like rational numbers, right? It only sends like integer stuff. Okay, that's a proof. Okay. Questions? So this is all like a recap from last class. But I'm happy to go back and talk about anything before we dive into applications? Okay. Yeah, please feel free to ask. Okay, otherwise, like the applications, they're probably not going to make sense. Okay. All right. So now let's look at applications. So here it won't be like essentially it'll be like I'll give you, we'll talk about a different algorithm problem, which just looks like, just like a different problem, but somehow we can solve it using a flow. Okay, so what's going to happen is we're going to give some problem, and somehow we're going to have to imagine what the flow graph looks like. Somehow if we find the max flow on this graph, it will solve the original problem. Okay. All right. Okay. But yeah, before we see applications, like one more time, any confusion about last class, max flow? I mean, it's okay to ask, like, okay, all right. So let's study the first application of flow. Okay, so it's called the matching problem. Okay, so you have a bunch of students, okay, on one side. Like you have a bunch of students, and you have a bunch of stuff on the other side, okay? Like this Bucks hat, jersey, whatever, swag gear, okay? And it's like, let's just say there's, some students, and there's only one of each, okay? So there's only one pair of shoes, one hoodie, and so on. And like, students have preferences, right? Like this person, would be happy with either the hat or the jersey. And this person would be happy with the shoes, the hoodie, or the t-shirt, okay? And there's only one of every stuff, okay? So, and the goal is to match the students with the items, okay? So obviously, right, two people can't have the hoodie because there's only one of the hoodie, okay? But we want to make as many people happy as possible, meaning we want to have matching from students to items that maximizes the amount of things matched, okay? That maximizes the amount of students that get some stuff, okay? Does the problem make sense? And if you have any like pre-med friends, every year there's you may hear called like a matching process, and what that is actually like somebody is running this problem where like one side is like student app or like whatever med students or residents or whatever, the other side is hospital slots, and somebody, right, there's an organization that gets paid lots of money to run some variant of this matching algorithm that I'm about to show you. Okay, so that's pretty cool. It's like one of the most used algorithms. But at least as a problem makes sense. Okay, we want to match students to stuff so that as many students get stuff as possible. Okay, questions? Okay, so for instance, like this is maybe one person is left out, but 1, 2, 3, 4 people are pretty happy, right? And it turns out I think this is the maximum matching. Okay. All right. Now we want, okay, so this is a very interesting problem, right? Now, the claim is that like this is actually a flow problem in disguise, okay? So now let's see. So what do we need for a flow problem, right? We need a graph, we need a source and a sink, right? And some capacities on the edges, okay? So the flow problem, so this will be like a very common technique of how to turn like a matching problem or these are called assignment problems into a flow problem. So first we need a source and a sink, okay? So this is how it's going to be. We're going to have a source that's going to connect to all the students, and let's direct all the edges, right? In flow, we need the edges to be directed. And then we're going to have a sink that connects to all the stuff, okay? And the intermediate edges are basically whatever the preference of the student was, right? We just kept them. We didn't change them, okay? All right, so now, okay, so that's the graph. Now we still need capacities on the edges, right? Any idea, like how to set those values? Like intuitively, right, we know that one student can only be matched with one stuff, right? Like you can't have a student get 2 things. Like that's not going to be okay. So we want to maximize the number of students that are happy. Yeah, any idea how to set the capacities? Yeah.
I guess like so every student has like 1, 2, maybe like 3 edges going off of them. So what I'm saying is that for one person, all of the edges that come out of them should add up to 1 or add to 1.
Right. Yeah. Exactly. So all the edges coming out should add up to 1. But how can we enforce that? Right? Because students have different amount of things coming out. Right? Like this person would be happy with 3 things. Some other people would be happy with 2 things. Some other person just wants 1 thing. How can we enforce that kind of only 1 unit of stuff comes out? Okay. Well, we have this edge, right? The amount of stuff going in. And what is flow, right? Flow requires us in equals out, right? So, oops. Okay. Oh, okay. I guess I already have it here. All the edges have capacity 1. Okay. And intuitively, why does that make sense? So before I present the formal proof, let me give you an intuition of what's happening. Okay, so all the edges have capacity 1, right? And we're saying, okay, I want to send as much unit of stuff or water, right, through from S to T, right? What's going to happen, right? Well, S is going to say, okay, all the edges have capacity 1. I'm going to try to send 1 on every edge, right? And then because in equals out, right, flow in equals out, every person will have at most one thing going out, right? It cannot be that this person will have all 3 edges with 1, right? Because there's only 1 unit of flow coming in at most, okay? So then that kind of enforces the fact that, like, you know, every student can only match with one thing. And that's also true on the other side, right? If every capacity is 1, then like 2 people cannot be matched here, right? Because if 2 people, let's say, you know, 2 people were matched to this hoodie, then they would have a flow of 2, right? But the capacity on this edge is 1, okay? So that's not, flow is not gonna let that happen, okay? So the max flow ends up looking like this, which is, you know, every edge has capacity 1, but some edges become saturated, right? Not every edge will become saturated because we're trying to find the best feasible flow, right? Some flows are not feasible, right? It's like I cannot send 1 to everything because like it won't make things work out, right? So we create this graph. We just run a flow algorithm on it, like for Wilkerson. We'll see different algorithms later. And then this is what's going to pop out, right? This will be the max flow, okay? And the claim is that if I just look at the edges that become saturated, that will give me the maximum matching of how to match students to swag. Okay? I'll show you a proof, but any questions about what just happened, like how the flow network was created, intuition of like why you'd want to do this? Essentially, we're trying to force the condition that every student only has one thing being, you know, one thing that they can match to. And the way we do that is by setting the capacity of the edges, right? So only once, you know, student has capacity 1, only one thing can go here and one thing can go out at most. And every item will have capacity 1, so only one thing can get matched to it. Okay. So why would a flow? So this is why it's important that the flow actually is the integer flow. Because if it's like 1/2, or 1/3, 1/3, 1/3, it'd be harder to interpret what that really means. But we know that max flow will be some integer, right? And because the capacities are 1, it's either going to be 0 or 1. Okay. So why does this work? Okay, so that's the key question. But okay, so let's break this down. Okay. Right, like I said, you know, all the capacities are 0 or 1, so the flow on every edge will be 0 or 1. Okay. We know that's like why I emphasize that, you know, if the capacities are integers, the flow will also be integer, okay? Right, like I said, stuff in equals stuff out. So the number of things that, you know, any student ends up like sending a flow to is at most 1. Okay, so that's great. And the claim is, like the key claim is, if we look at the edges that are saturated, they form a matching, meaning every student is at most 1 and every item gets at most 1, right? Does that make sense why? It's just because of the, you know, if there were 2 things matched to this, that wouldn't, like the capacity wouldn't, you know, wouldn't make sense, right? It would be 2 and 1. That wouldn't be flow in equals flow out, okay? All right. And then like how do we say, okay, how many students got matched? Well, that would just be the value of the flow. So what we can do is we can just look at this cut, right, and say, okay, how many things ended up going to T? That's going to be 4 in this case. Yeah, and yeah, basically, you know, the max flow will correspond to a max matching, right? So another way to say it is, imagine any matching of students to items. That corresponds to some flow, okay? So, you know, if whatever way I match, let's say I only match this student to the Bucks jersey, right? That corresponds to some flow, right? Where you say 1 here, and 1, okay? Because every matching is a flow and every flow is a matching, the max flow has to be the maximum matching, okay? Questions? So, you know, it's pretty cool, right? Like this matching problem, if I just give that to you in the beginning of the semester, you have no idea how to solve it. Like you'll just like try to case by case, like maybe go say, but now it's like almost a trivial application of this flow. Just run a flow network, it'll give you the maximum matching. Questions? Yeah, if you don't understand why, how we ended up, finding this, like that's a good time to ask. Why, yeah, you should know like why flow is giving you the best way to match things. Yeah. Interesting. Okay. No questions. Okay. Yeah. Please feel free to ask. Like it's if you're okay. All right. All right, so intuitively, like kind of what these flow problems are good at is they're really good at these assignment problems where you want to assign some things to some other things, and like you have some constraint, like you can imagine like if there were 2 copies of the hoodie. Let's say there's 2 copies of hoodie, but only one student's on this side, but for some reason there's 2 hoodies. How would we change this to solve that problem? Let's just say I had 2 hoodies. Or let's say I have 2 of all the, how do I change the problem? How do I change the flow problem to solve that? Let's say I have 2 of every item. Yeah. Yeah, but which capacities? But every student, let's say, can only get 1 item. But let's say I have 2 hoodies. I still want that every student can only have 1 item, let's say, to be fair. But there's 2 hoodies now. Yeah, sorry, go ahead. Yeah, exactly. You just change this capacity to be 2, right? So everything else will stay 1. But that would mean that like, 2 things can come in now, right? And 2 things can go out. Okay. So that's why like it's such a flexible way to have these assignment problems. Like any assignment problem you can think of, you can model with flow. Okay. All right. So yeah, hopefully that made sense. Like we just changed some capacities. Okay. Questions? All right. So now let's look at a more complicated assignment problem. Okay. We're going to be looking at more and more complicated assignment problems. All right. Okay, now you have students and ice cream. Okay, we all love ice cream here, and it's just also we want to say, okay, we have some ice cream, right, finite amount, like, and we have a bunch of students, and every student wants to eat a certain number of scoops. Okay, so like some students really love ice cream and they want a lot of scoops, and some students, they're just happy with 1 scoop. Okay, but of course, right, every container of ice cream has a certain number of scoops, right? And also the students have preferences, okay? So like, I may want to eat 4 scoops of ice cream, but at most 2 of them can be chocolate, okay? I like chocolate, but not that much, so at most 2 chocolate, okay? And the question is, okay, I have a bunch of students with all these like, constraints, like, which flavors they like, how many they want, and I have a bunch of actual ice cream, right? Question is it possible to like satisfy all the students, okay? And you can imagine, right, this is just some made up problem, but you can imagine how like this kind of problem would be useful, right? So for instance, this is a optimization problem that's solved every day, which is like you have a bunch of planes and they need to land in certain airports, and you say, okay, there's only this, like some matching between like, okay, how many people want to fly out of it versus how many people want to fly in, right? So you can kind of imagine why these things are useful. So let's kind of write it as a graph, right? Okay, so on this side you have students, and on this side you have ice cream, and these big numbers that say how many scoops of ice cream is in every tub, right? So some tubs are huge, they have 10, but some are small, right, 3. And this just says like, okay, how many scoops of ice cream that they want, okay? So it's like, and basically, it's the same as before, okay? So here the constraint, the capacity just says, okay, there's only 6 scoops of ice cream here. So like, whatever students get here, right? You can't have more than 6 scoops of ice cream being taken out. So what? Sorry, this person wants 1 scoop of ice cream, chocolate, or yeah. Okay. All right. Yeah, I guess I don't have much to say, but like, do these numbers make sense? It's like saying, okay, this person wants 10 scoops, and they would be happy with like 5 of this or 10 of this. Okay. Or this person wants 1 scoop, but they want 1 chocolate, at most 1 chocolate, and at most 1 vanilla. Okay. So, or this person wants 4 scoops, but what they really want is like 3 scoops of this flavor and 1 scoop of this flavor. Okay. All right. So, just right, putting those constraints as capacities on the edges. Okay. And then we just run flow. Okay. And basically, kind of like as before, the value of the flow tells you like how much scoop every person is getting. Okay. And right, like we already encoded the constraint that somehow like because the capacity here was 6, right? Kind of more than 6 scoops cannot be taken out of here, right? And because the constraint here was 3, right? I cannot like feed this person 100 scoops of ice cream, and because it's the capacity here is 1, I'm not going to give this person like 2 scoops of chocolate. Okay, so somehow these capacities are just like enforcing these constraints. Okay, does that make sense? It's the same as the assignment problem or like the matching problem, but now, now there's just imagine like it's the same like this is a hat, this is a hoodie, but there's like multiple copies of the hoodies now. But those are the scoops, okay? And some people want, they'd be happy with at most 2 scoops of lemon, okay? All right. Okay, so any questions? Yeah, like because we have the capacity of this edge is 10, at most 10 scoops will be given to this student, right? Because, like I said, because we have a capacity of 1, I'm not going to give this student 2 scoops of chocolate. Okay? And really, the thing you have to check is like, right? Is the optimal assignment an example of a flow on the graph? Okay, and turns out it is. So that means the max flow, right, is the best assignment. Okay. That's all this is saying. Yeah. All right. Pretty straightforward. Questions about where these like numbers came from? Yeah. Yeah. So capacity is just like, right, it's just like saying what is the maximum thing that can travel on any edge, right? So it's just like imagine pipes, right? Like some pipes can be big, some pipes can be small. But really the thing that matters is like the water in has to be equal to water out, okay? Yeah, so the capacities can be whatever, right? Capacity is a property of the graph. But flow is like, right, flow is something I'm doing on top of the graph. And the flow, for the flow it has to be in equals out. But the capacity can be anything, yeah. All right, does this make sense? Questions? Yeah.
So I guess this is asking, the question is asking like assign as many matches as possible. It's not asking like will it like satisfy the most number of students. Like this won't give you that, right?
So what will this give you, right? This will give you the maximum number of scoops that will be served, okay? Because that's what the flow is measuring, right? It's like saying, okay, what is the maximum number of scoops that I have served to students, okay? That's what this is maximizing, yeah. Previously it was how many students were matched. Here it's like, because the capacities, they're really representing scoops. What this is maximizing is the most number of scoops that are served. But like, you can also use that to check like, okay, is there, let's say like something you can check is, does every student get exactly what they want? Like, this person got 1 in 10 scoops. Well, like, that's, or like, is there an assignment where every student gets the maximum amount of scoops they want? And that's not true, right? You can just check the flow value. is going to be less than the sum of these, numbers. And then you know that, like, hey, not every student got exactly what they wanted. Okay, so you can also do this. Yeah. No. So yeah, so that's the thing. Like, solution to flow may not be unique. So there could be multiple flows that achieve the same value. So let's go back to the easier assignment problem. Like, there could be actually another way to match 4 things, like 4 students to items. So this name may not be unique, but the fact that it's 4, it's like the best value. You cannot do 5. Yeah. Okay, so now, yeah, just go home and think about this assignment problem. It's a very general problem, right? It was saying, there's some resource on this side, there's some demand on this side. You want to check if the demand will match, or like the resources will match the demands. Okay. All right. Now let's see a fun example. Okay, so this is pretty fun. Okay. So this is not an assignment problem. This is a sports problem. Okay, so all right, let's say you have these 5 baseball teams. Okay, and they all play against each other, right? So on the right side is just like how many games they have against each other left. Okay, so this means New York and Baltimore, they have 5 games left against each other. Okay, and they have a current win-loss standing, right? Like, basically how many times they've won, how many times losses, and sort of how many games there are left to play, right? So if I, everybody has, 28 games left to play, and I didn't show you the other teams, right? There's also teams in other things, so that's why this number is high. But the thing that's important is, like, among these teams, there's also some number of games they have left to play with each other. Okay, and the question is, when can I guarantee that a team can never be first? When is a team eliminated? Okay, so let's say a team is eliminated if can never, whatever the rest of the games play out, it can never be first place. Okay, so for instance, right, if I told you this team had 0 wins and only had 28 games left to play, it's already eliminated, right? That's very easy. But like for certain values, it's not so clear, right? Because there's all these like complicated schedules one can come up with, right? And the question is, when do I know when a team is eliminated? Okay. So the problem is, right, how do I, if I give you a certain number of wins and losses that this, or like if I give you a certain number of wins that this team has, how do I know that it's already, like, it's in contention to be first, or does it have like no chance to ever be first? Okay. So for instance, right, if I told you this Detroit has like 0 wins so far, there's no way, right? It's like way less than 75 because it can only win 28 more games. Okay. All right. So does the problem make sense? So I'm going to tell you a certain value of wins, and the problem is, if I tell you a certain value of wins, can I determine, is there some schedule where it's possible for a Detroit to be, let's say, first place or join first place in terms of number of wins? Okay. So that's the problem. All right. Okay, so what is a naive way to check? Well, naively, right, like if I tell you a certain number of wins and I add that to the number of games they have left, that's the best case situation. And if that's already less than the win total of some other team, then they can never be first place, right? So that's pretty easy to check. But in certain situations, it's actually not so clear, okay? So here is one example, right? Let's say if I told you Detroit's win record was 46 wins here. Can it ever be first in wins? If I tell you, okay, it has 28 more games to play, and like among these 5 teams, there's some number of games that they have to play with each other. Okay. Well, 46 is pretty easy because it only has 28 games left. So if I add 46 plus 28, that's 74, right? It's already less than 75. So if I tell you it only won 46 games so far, it can never be first place, right? Does that make sense? That's the same reasoning as before. Okay. This is, of course, like that's a sufficient condition, but not necessary. Okay, so we'll see. What if I told you at that point Detroit had won 47 games? Then it's not secure, right? Because 47 plus 28 is 75, I think. Or 47 plus 28, well, it has to be an odd number, so I think it's 75. And it's not so clear, right? Like, can someone tell me, like, is that team, does it ever have hope of being first place? If I told you at this stage of the table, it has won 47 games. So let's look at these two teams, right? How many games do they have left to play against each other? They have 5 games, okay? So at some point, one of these teams will have 76 wins, right? Because they have 5 games between them left, right? So at least one of these will have 76 wins. So actually, if I told you Detroit has 47 wins, it cannot be in contention for first place. Does that make sense? Right? Right. So the previous logic doesn't work because, like, we get exactly 75. But right, there's some more complicated logic we can do, right? Which is these first 2 place teams, they have actually a bunch of games left with each other. Even in the worst case, one of them will end up with 76 wins. Okay. So then it's still eliminated. Okay. But now I can ask like even a harder question, right? Okay, but if I give you an arbitrary value like 50 wins, how do I know if it's eliminated at this place or not? Okay. So the hardest example turns out to be 48. If I told you at this stage of the table, Detroit had 48 wins, and I give you like, okay, it had 28 games left to play overall, and then among these teams, it has some number of games between them. Can it ever be first place? Okay. All right. So that's the problem, okay? So does everyone understand what the problem is? I'm telling you this team has 48 wins at this stage of the game, or like whatever table, and then like the question is, can it ever be first place? Or joint first place, let's say. Okay. It's not so easy because, right, like, I mean, if you follow sports, it's like so complicated, right? Okay, this person can win, there's a tiebreaker, whatever, right? But at least in this simple scenario, right, where there's no ties, like, we just care about wins, we can solve this using flow, okay? That's the cool part, okay? First, does everyone understand the problem? Like, does the statement of the problem make sense? If not, please ask. Okay, so that's the problem, okay? So, right, like I said, flow, we need a graph, okay? There's no graph here, so we need to create a graph. Okay? So, so first, let's make a simplification, right? Well, we know that we're trying to like help this team as much as possible, right? So we can assume, right, that they win all their remaining games, okay? That we can assume for free, right? Because like that can only help them, okay? So it's going to end up with 76 wins, okay? And the question is, can any other team reach more? At least, is there some team that will reach 77 wins? Okay, that's what we're trying to figure out. Okay, does that make sense? So we can just assume it wins all the games, okay, of its own game. But the question really is, among these 4 teams, can one of them reach 77 wins? Because they play against with each other, right? They don't just play with this team, right? Another way to say is there some outcome where every team ends up with at most 76 wins? That's the same question, right? Because if that, then there's hope of Detroit being in joint first place. Even though I'm not asking whether it's likely or not. I'm saying, is there a chance? Is there some realization of wins and losses where it can possibly end up? Okay. Right. So what I did so far is saying, right, I said, okay, assume it's 48 here. We can also assume it wins all of its remaining games. That only helps it. So really the question is there a way to like rig the system, let's say, with wins and losses where every other team ends up with at most 76? Okay, so that's the problem. Okay. And really, like, what makes it hard is like these teams play against each other, right? So like one of them has to win. So like trying to make sure everybody is kind of down at the same time. Okay. And the intuition is like we're going to set the capacity of the edges in some graph to kind of force that like no team will end up with more than 76 wins, okay? All right. So really the idea is like this is also an assignment problem in disguise. So what is being assigned is like these 4 teams on top, they have some number of games between each other, right? We need to assign a winner to every game, okay? So it's like we want to assign it's like items, right? Like you imagine every game they're playing is an item. We want to assign it to one person or one team or the other that participate in the game. We want to make sure that no team ends up with more than 76 wins, okay? So now let me walk you through this flow graph, okay? So let's just say start simple, okay? So there's a source and a sink, okay? So that we need, we add that. And now, what are these nodes? Okay. These are not nodes of teams. These are actually nodes of pairs of teams. Okay. So there's a node for a 1-2 pair, 1-3 pair, 2-3 pair, 1-4 pair, 2-4, and a 3-4 pair. And the reason is like every pair, right, among the first 4 teams, they play some number of games with each other. Okay. And it turns out if you look at the table, this 2-3 pair, right? This team 1 and team 3 have 7 games left between them. Okay. Now on this side, we have the teams, okay, these 4 teams. And what's kind of the idea is, right, every pair needs to play some number of games. So look at the 3-4 pair only connects to the 3 node and the 4 node, okay? The 2-4 pair only connects to the 2 node and the 4 node. The idea is we want to assign the remaining games between the pairs to one of them, right? So there's 4 games left between team 3 and team 4. One of them has to get some, all those 4 games, somebody has to win, either team 3 or team 4. We want to assign that. So that's the idea in building this graph, right? And now what are these numbers, okay? So I told you how the graph is built. I haven't told you what the numbers are yet, okay? So basically the graph is just build a way to assign, for every team, what kind of matchup it participates in, okay? So that's what this graph is capturing. And now the capacities on these edges are just like how many games are left between every pair, okay? So like I said, 3-4 pair has 4 games left, and some different pairs have different number of games left. Okay. And the idea is like, for every game between every pair, I need to give it to one side or the other. Okay, I need to give the wins to one. So that's why the capacity is there. And now, what are these numbers? Okay, right. Ultimately, I want to enforce that every team ends up with at most 76 wins. Okay, because otherwise, right, like Detroit has no chance of ever being first place. So whatever this thing is this number is saying, okay, I look at the number of wins 4 already has, and I say, okay, what is the maximum amount of wins that it can ever gain? Okay, so it turns out, if I look at team number 4, it can only gain 13 more wins, and that's when it gets to 76. Okay, or if you remember the first team, right, it already was at 75 games, so it can only win 1 more game. So it's saying, right, among the pairs that it participates in, right, so look, what pairs does 1 participate in? It participates in the 1-2 pair, the 1-3 pair, 1-3 pair, and 1-4 pair. Among these 3 pairs of matchups, hopefully it only gains 1 more win, okay? If it only can gain 1 more win, because if it gains 2 wins, then already, right, it gets 77, and then Detroit can never be first place, okay? So that's where these numbers are coming from. And then what are the capacity of the middle part? We just set it to be a super large number, okay? Like you can just imagine it's unbounded, infinity. Basically, the capacity of the middle part don't really matter here. We can set them to be as big as possible. Really, the thing coming in and going out are kind of enforcing some constraints, right? The thing coming in is saying, oh, the 3-4 pair only has 4 games between them, right? So I have to kind of dole out these 4 wins to either the 3 or the 4. But at the end of the day, I want team 3 to only accumulate 7 more wins across all the pairs that it participates in. Because if it gets anything more, I'm screwed, right? It gets to 77 games, 77 wins. Okay. So that's where these numbers are coming from. Any questions? And then so it's pretty much like this assignment problem. Now we just run flow, okay? Right, like I say, how did this number come up? Well, Toronto already has 63, right? We know Detroit can only get up to 76. So it better have this capacity of 13, because if it was somehow getting 14 wins, it'll already be way more than what this team can get, okay? All right. Like I said, right, these numbers are just set up so that these teams will be bottlenecked by 76, okay? That's the idea. And like I said, edges in between don't really matter. And then we just run flow from S to T, okay? So I kind of explained already, but can someone summarize why this works? So you have to check, right? Basically, there's 2 things we have to check. One is a flow corresponds to a valid way to assign games, okay? Well, that's true, right? Because, 2 and 4 is only connected to 2 and 4, right? Either the wins here has to go to 2 or 4 only. And you have to check a valid schedule corresponds to a flow, which is also kind of the same reasoning, okay? So then what are we going to do, right? We're going to run flow, max flow from S to T, and we have to check, is every edge leaving S saturated? If it's saturated, then there is a way to assign wins and losses, okay? If it's not saturated, then that means this schedule is not possible, okay? So if it's not saturated, it's saying, oh, actually, like, maybe this edge wasn't saturated. It's saying, oh, actually, if I give out one more game to this pair, someone's going to cross the threshold. I'm screwed, okay? And really, the reason this works is like, it's like matching almost, right? It's like saying every flow corresponds to a valid schedule, okay? That's why this works. And then we just check, like, oh, did S send out all the flow here? That's how we just check the value of the max flow, right? If we check the value of the max flow, and actually if we just look at which edges become saturated and the value of the flow in them, that tells you, like if this edge had a 2 and this edge had a 2, this means, oh, among the 4 games that 1 and 4 will play, 2 of them I'll assign the winner to 1, and 2 of them I'll assign the winner to 4, okay? That's what this means. All right. Now let's actually check. Okay? So this was, I started with a concrete number, right? Like 48. Is it possible for Detroit to ever be in first place? And we can actually run this flow on this graph, okay? It's not too big. And here, right, okay, I didn't really run the flow. I said, okay, actually, I'm going to give you a cut, okay? That's the same thing, right? Right? A value of a cut is actually, always at least as big as the value of the flow, right? Max flow equals min cut. So consider this cut, okay? So this cut looks like this. What is the value of this cut? What is the capacity of this cut? Right, so what is the total number of edges that go from one side to the other, right? So these 3 edges get cut, that's 12, and then these 3 edges get cut. So it turns out that value is 25, okay? Why is that a problem? So I told you there's a cut of value 25. What is the sum of these edges here, these edges leaving S? So that is, right, that's 12, 14, 15, that's 20, plus 7, 27, okay? So is it ever possible for Detroit to win? So can someone give me an upper bound on the max flow here? Right, I told you there was a cut of value 25. So what is an upper bound on the max flow? It's at most 25, right? But I told you these are the number of games remaining, 27. So is it ever possible for this schedule to exist? The answer is no, okay? That's how you can check whether it's ever possible for Detroit to ever be number 1. The max flow is at most 25 here, but I know I have like 27 games left that come out of S. That means I cannot assign this while respecting the edge capacities. So that means this is not possible, okay? Because if it was possible, it would correspond to some flow, okay? So this is the logic, okay? If it was possible to assign these games, right, so everybody is capped at 76 wins, then it would correspond to some flow, okay? That means the value of the flow would be at least, whatever, 27, but I demonstrated a cut, right, in this graph. I didn't have to run flow at all. I demonstrated a cut, value 25. So the flow can never be more than 25, right? That means it's not possible to assign this schedule, okay? Questions? Yeah.
So you said that this cut is the max cut. Is that
No, right? This is a cut. I'm just giving you a cut. It's at least as big as the min cut, right? Because it's a cut. This cut has value 25. That means the min cut can only be smaller, right? So at least 25 or 25 or below. That means the flow can never be bigger than 25, right? Because max flow equals min cut. Because the flow can never be more than 25, I look at, okay, how many games has S, I need to, like, how many games do I need to fix, right? Well, I count, right? 1, 2 pair has 5 games left, 1, 3 pair has 7 games left, 2, 3 pair has 2 games left. If I sum this up, I think that's 27, okay? That's more than 25. So that means, right, ideally, if I was able to find some schedule of wins and losses, this flow would be 27, because that's the number of games left that I need to assign. but I demonstrated a cut of value 25. So there can be no flow of more than 25, right? Because max flow equals min cut. This cut is even, at least is, min cut is the smallest cut, right? This is a cut. Min cut can only be even smaller. That means the flow can never be more than 25. And that's bad because that means, right, that's not enough games, right? I still have 27 games here. So that means the flow, yeah, that just means it's not possible to assign this. Like there's no possible way to even, rig the wins and losses between the other teams. Some team will end up with at least 77 wins, okay? This is not so obvious, right? If I just give you a table, it'll take you like 2 hours to figure that out. But I just drew a graph and I demonstrated a cut, okay? And I say, okay, this cut proves to you that this schedule is not possible. Like Detroit can never be first place, okay? That's pretty cool. Actually, this cut actually tells you something a little bit interesting. So this is for personal entertainment. Okay, let me just finish the thought, which is, right, so max flow cannot saturate all the edges coming out of S, meaning like there are some games that are not to be assigned, right? I can assign them. That means Detroit can never have joint top wins, okay? So this cut actually tells you a clever way to check. So this is just for fun, right? This cut was like, if I look at the cut, this cut involved 1, 2, and 3 nodes, right? Teams 1, 2, and 3, okay? So if I look at just teams 1, 2, and 3, the total number of wins among them is 215 if I sum up these 3 numbers. And they have 14 games left to play with each other if I add these numbers. So that means at some point, right, there's 229 wins that are left that are among those 3 things, right? So at least one of them will have at least 1/3 of them, which is 77. Okay? So that's also another way. So the cut actually tells you to look at the subset of teams where one of them will be guaranteed. Like that subset has too many wins among themselves if I add up all the wins, okay? So that's another fun kind of thing you can tease out of this cut. But yeah. Okay. Any comments, questions? But yeah, this was just an assignment problem in disguise, right? I just wanted to assign for every team. It can only participate in a certain number of items, right? The items it can participate is, well, the matchups that involve the team. And I have some number of, things that I need to send through that matchup. And then I can only, every team is bottlenecked by some number of wins. And I just check, is it possible to satisfy those constraints, okay? All right. Okay, so that's more complicated example of assignment problem, but pretty cool. Questions? Okay. Yeah, if this doesn't make sense, like I'm happy to go back. Yeah. Okay. All right. So now let's move a little bit more complicated assignment problem now. Okay. So this is kind of increasing the power of flow. Okay. All right. So this is a pretty abstract problem. Okay. So let's say I have a bunch of jobs. Okay. So every node represents a job or a task, and the number on the node represents how much money I make if I do this task. Okay? So some jobs actually cost you money. Like let's say this is to like carry a bunch of heavy stuff, right? So it has a toll on your body. So it's like -1. Okay? What do these the arrows mean? It means this job that represents this, or the task that this node represents, can only be done after this task is done. Okay? So it's like every job is pointing to a job that must be completed before it can be completed. Okay? So that's the definition here. So it's like, for instance, right, if you do this, in order to do this job, you actually have to do this job first. In order to do this job, you have to have finished this first. You have to have finished this first, and you have to have finished this first. Okay? So there's some dependencies. Like every task is pointing to all the tasks that must be done. Right? Okay. And the question is, how do I pick a subset of tasks to do that maximize the money I get? Okay, like right? So for instance, let's say I do these 4 jobs. Okay. Oh, sorry. I guess I have to do these 1, 2, 3, 5 things. Well, then the money I get is that's minus 11, but 4 plus 3, that's 7, 8, 9. Okay, I probably shouldn't do this, right? That's like gives me minus value. But right, I actually want to go here, right? Because this task is like 14. So maybe I just do this one, right? That already gives me 14. But like, if I want to do this task, that's nice. But first, then I have to do this one and this one. Okay, so there's certain like trade-offs that you have to make. Okay, so the question is, I want to pick a subset of tasks to do that gives me the most amount of profit, while respecting the constraint that, right, if I do a task on a node, I must have done everything that it points to. Okay, does the problem make sense? Okay, so this also seems like a hard problem, right? Like, how would I go about picking the best thing? Turns out you can solve it using flow. Okay. Questions about the problem? I say this is a pretty advanced example. So most of the things that you'll see maybe in a test will be just like assignment, like I have some items to assign, give some constraints, maybe change the edges. So there's a homework going out today, and then you'll see like lots of other fun examples of flow. Okay. But let's just see this again. Okay. So I need to add a source and a sink, right? So that's the S and T. The question is, how do I connect them to the rest of the graph? Okay. So it's going to be a little bit non-obvious this time, right? Previously, it was kind of obvious like how you connect them. It was just like the bottleneck on, it was like every team can only have this many wins, so you add that as a constraint. Here it's going to be a little bit non-obvious. So okay, I'm going to connect S to every node that has a positive dollar amount, okay? And the capacity of that edge will be that positive dollar amount, okay? So for instance, S is not connecting to this -1 thing because it has a minus dollar amount. So I only connected the positive dollar amounts. And likewise, I connect all the minus dollar amounts to T, where the value will be 5, okay? Which would just be like, it's like the minus of the value, okay? And kind of the high level idea of what's happening is like, before I show you, what are the rest of the numbers on the rest of the edges, kind of like we want a minimum cut in this graph to represent the tasks that we do, okay? So what will happen is I'll set up a graph, I'll find a flow, I'll actually show you a minimum cut, and that minimum cut will actually, one side of the cut will be all the tasks that you should be doing, okay? Somehow we're going to magically like put numbers so that will be true, okay? But first we have this constraint that like, let's go back a little bit, right? Like, if I take this task, I better be doing this task, right? So I don't want like things that point to be on different sides of the cut, okay? I don't want jobs to be cut. So what that means is I set the capacities of all these intermediate nodes, edges, to be plus some super large number, okay? Infinity. And the reason is like, I don't want those, turns out, do I do plus infinity or minus infinity? Oh yeah, plus up. Yeah, because I don't want those edges to be cut, okay? Because if I cut, I'll show you, instead of flow, we're going to be looking at min cut. So intuitively, I kind of want, what's going to happen is I want to separate all the nodes, jobs that I'm going to do with everything else. And I don't want any job that I do to be pointing to something here, because that's bad. That would not satisfy my constraint. So what I do is I'm going to set the capacity of all the edges actually in the graph to be plus infinity, okay? Some super large number. And the idea is going to be that the minimum cut that's on the S side is going to correspond to all the jobs that I'm actually going to do, okay? So because I can always choose to not do anything, right? Get value 0. That means I'm never going to separate two nodes where one points to the other, right? Because that has a minimum cut value of infinity, right? A super large number. But there's already a cut that's 0, right? Which is, or like there's already a cut that's not infinity. So basically, by adding that like infinity constraint, I will never like put 12 on one side, meaning the jobs that I do, and 14 on the other side, okay? And we'll see how that's going to work. But that's the main idea, okay? Like, I want a cut that's part of S, that's on the S side, like all the nodes on that part of the cut, to correspond to the jobs that I'll actually end up doing, okay? All right. So that's okay. So we're going to have to check some math, but first let's check, okay? Is there a non-infinity cut in this graph? Well, there is, right? If I just cut all these edges, right? That's how I separate S and T. Cut all these edges. Well, the value is some positive value, right? It's basically sum of all the nodes where the profit was positive, right? That's how I define these edges. So that kind of tells me that like, that's one cut. If I look at the minimum cut, I'm never going to be cutting a positive infinity edge, okay? Because there's already a better cut, right? So this cut will correspond to me doing no jobs, okay? Somehow I want to say, like, is there a way to pull some nodes on the S side where, like, I don't cut any of these, like, required edges, right? I don't cut any edge where one points to the other, because that would be bad, right? That would mean, like, oh, I'm doing jobs where I don't do the things that's required. I don't want that, okay? All right. But now let's look at some other cut, okay? So let's look at this cut, okay? As long as that a cut is not crossing one of these like predecessor edges, it's going to have a finite value, okay? Its value is going to be determined by these edges, okay? It's kind of like saying, well, intuitively I want all the jobs that I do to be on the side of S. That means I have to potentially take on some minus profit jobs, and I want to like capture that, okay? So essentially the calculation is going to be is the value of a cut will be this value big C, okay? So big C I'm going to define as the sum of all the positive values, some fixed number, minus the profit that I get, okay? And the intuitive reason is that every time I pull a node to the side of S, right, I'm like not cutting an edge, right, that represents its profit, okay? So that means I'm going to subtract it from this value C, right? C is the sum of all these edges. So if I pull this like 4 node to the S side, then I'm not cutting this edge. So that's why the capacity of a cut, or like the value of a cut, will be this fixed value C minus the profit that I get, okay? And that kind of makes sense, right? Like if I ever pull, let's say I only pull let's say one of these nodes on this side, but none of the edges that it points to, then that's already like a positive infinity thing, okay? And the profit I get is negative infinity, right? I can't do that. So that's why like the capacity of a cut is C minus the profit, okay? It's like every time I pull in a node to the side of S, I'm not cutting that edge, okay? That's the intuition. I'll show you the formal calculation. But at least if you believe this, okay? If you believe that I've set up the graph so that the value of every cut on the S side is actually C, this fixed constant, minus the profit, then it makes sense why I want the minimum cut, right? If I have the minimum cut, then I maximize the profit, okay? So you may not believe that like this holds, but if you believe that this holds, do you see why we want the minimum cut? Okay, I've cooked up the graph so that the value of a cut is basically minus profit. So because I want to maximize profit, I want to minimize the cut, okay? Questions? I'll show you why this is true. That was kind of hand-wavy, but if you, let's just say you believe that I've, cooked up these edges so that the value of a cut on that, that includes S, is C minus the profit that I get, then it makes sense, right? I want to minimize the cut because then I will maximize the profit, okay? So as you see, like with all these flow applications, it's always like, what is the graph that I'm creating, okay? That's the idea. Well, then, of course, I can solve this with flow. Really, the question is, like, why is this true, okay? Why is it true that the capacity of the cut is equal to this minus profit, right? That's like the key claim, okay? And, if you have this claim, then, like, it's pretty obvious what you should do. Well, just find the minimum cut. Because this is a fixed constant, the minimum cut will maximize the profit, right? Minimum is going to be super negative, but that means a profit that's super high. And so you can do this with flow. And kind of the main idea is like every time you pull a node on the S side, you're not cutting that edge from S to that node. So you're like subtracting that away from this quantity C, okay? Where you're actually doing that job, right? So that's why it's C minus the profit, okay? All right? But let's just check the math, okay? All right. Why is it true that the capacity of the cut is C minus the if I do all the jobs on the vertices that are on the S side, why is it C minus the profit? Well, intuitively, right, like which edges can I cut in this graph, right? I cannot cut this infinity edges, okay? Like that you can convince yourself, like I will never cut this infinity edges. So the only edges I'm cutting are the ones that point to t or the ones that come out from S, okay? Okay. And right, if you just, because jobs have positive profit and negative profit, that's why like you have to do this S trick and the T trick. But you can just check like, okay, let's just look at all the, actually I can explain it by words. Like let's look at, S to 2, right? 2 has a positive profit of 2, this node. If I were to bring it to the side of S, I'm not going to capture that in the cut. So that's going to be subtracted from this value C, okay? That's going to be subtracted because it's a positive value, okay? If I pull it to the S side, I can't, it's not going to participate in the cut. So that's why like I'm subtracting from this. But like for the negative ones, right, if I pull it to the side of S, I need to say, oh, I'm getting the negative, negative profit. And that's going to be captured by this edge. Because if I pull this minus 13 to the S side, the edge that I cut is this cut, right? Okay. So that's essentially what this math is saying, which is for all the edges that point to t, right, I'm actually getting the negative profit for them. For all the edges that, that S points to, I'm getting positive profit. But because I'm like, subtracting that, that's why this minus sign appears. That's why you get C minus the profit. But anyways, this is some math that you can follow, but intuitively it's like anytime I pull something on the S side, I cannot cut that edge. And if I pull a negative thing on the S side, I'm cutting the edge from that negative thing to the T thing. Okay? So that's kind of re-recording the fact that I'm getting either positive profit or negative profit. Okay? But just some calculation that the capacity of any cut is some fixed value minus the profit. Okay? That's why I want to find the minimum cut, because then I'll maximize the profit. Okay? Questions? But really the intuition should be from this graph. Okay? Questions? Yeah. Okay. So this is a complicated example, but now we'll see. I have some time, right? Now we'll see a slightly less complicated but cool example on the board. Okay. So let me just. So now it's another like matching problem, but this is going to be called a perfect matching, okay? Perfect matching. Okay. So what is a perfect matching? So let's say I have n, students. Let's say as before, n students, and I have n items. Okay. So it's, in this case, it's 4. And then I have some like connection between students and items saying, if they, if there's an edge here, it means this student would be happy with this item, okay? The question is, when is it possible to match every student with an item, okay? So if I have like the same number of students as items, right? A perfect matching is basically like you're saying, okay, every item goes to one student and every student goes to one item, right? It's like a perfect harmony, okay? That's called perfect matching, okay? So the surprising thing that we'll show is the following, which is, okay, so this is a bipartite graph, right? This is a bipartite graph, right? If I, if I draw the edges that represent, let's say there's these edges, and then let's say, just one example of a bipartite graph. The surprising thing is that, let me see if this marker is better. The surprising, okay, clearly not. Okay, the surprising thing is like, if every node, okay, I'll just do black. I think that's best to see. If every node has the same degree d, like some value, right? So I have n nodes on both sides. Let's say they all have the same degree d. So here d is 2, right? Every node on both sides has the degree same. But let's just say some number d, and everybody has the same degree. Then there's always a perfect matching. Okay? Then always perfect matching. Okay? So it's hard to see, but let me just explain, right? So it's like I have this graph, right? And there's some items, so students and items. Every student is like has an edge to all the items they'd be happy with. I want to say, and I have n students and n items, right? So in the ideal world, right, every student gets one item, right? I want to say, when can I always guarantee this assignment? Like there's some way to assign items to students so they get what they want, what they're happy with, but everybody gets one thing, okay? And the claim is, as long as the degrees are the same, there's always a way to do this, no matter how the internal things are connected, okay? So that's the cool thing. Like, it's like saying, I don't really care how the internal connections happen. As long as all the degrees are the same, then there will always be perfect matching, okay? So you may have seen this in discrete math. It's like a pretty fundamental theorem. But we're going to prove this using flow, okay? Any questions so far? Like, does the statement make sense? So here, here the perfect matching is pretty clear, right? Let's say I go this way, this way, this way, this way, right? So for this particular example, it's clear. But I'm saying, right, I have n is the arbitrary number, right, of nodes. As long as every node has the same degree, then I'm always guaranteed that some perfect matching exists. I don't even have to look at the connections. I just know that there will always be a way to match. Okay, so this is a surprising theorem, but it's like a very easy consequence of flow. Okay. Okay, so so the way we're going to do that is we're going to write any ideas or thoughts, like how can we use flow to show that a large matching exists? Like first we need a graph, right? Like a graph where there's flow. So we need a source and a sink. Any ideas about how to add them? Like what did we just see, right, in all these examples? Yeah, let's go. Yeah. Yeah. So we're going to just add an s and a t, okay? So everything here will be connected to an s. Right, and everything here will be connected to t. And because it's matching, right? What are the capacities on the edges? How do I put them? I just put 1, okay? So essentially, it's kind of the same as the first example. I put all the capacities as 1, essentially because I only want one student to be matched to one item, okay? So that at least enforces that, you can't have a student getting two things or two things being assigned to, one thing being assigned to two students, okay? So all the capacities are 1. But still, it's not clear, right, that there's always a way to get matching of size n, right, where every student gets one item, okay? So the way to do that is I'm going to show you a flow of value n, okay? In this, no matter how the internal connections are, there will always be a flow of value n, okay? So that's the first step. I'll show you a flow of value n. It's not going to be an it's not going to be a flow where every edge has a whole number, okay? It's actually going to have fractions. But what do I know about what do I know from the Ford-Fulkerson algorithm? There's always a max flow where the edges have integer values. So that's the cool thing, right? I just have to demonstrate any flow. It can have real numbers, rational numbers of large value. And I'm guaranteed there's an integer flow of at least that value. Right? And so what will happen is I'll show you a flow of value n. It's going to have rational numbers. So it's not an integer. It doesn't correspond to a nice matching. But then that certifies a lower bound on the flow, right? That means when I run Ford-Fulkerson, because all the capacities are integers, I will find a flow of at least value n, and it will be integer, and it will form a matching. Okay, so that's the cool part. So it's pretty. So okay, what do I do, right? So I have capacity 1 on every edge here. Okay, I have capacity 1 on all the edges. Well, I need to certify a flow, right? So the flow is going to be like this. Okay, I'm going to say, okay, the source will send 1 to every node here. Okay, that's what I want. But I want to say, okay, how does it go out? Well, I don't want to look at the connections. Okay, the connections are. If you're having trouble seeing, you should come closer, by the way. because like, the marker is not so good. So right, I have flow 1 to every node. What I'm going to do is it's going to send, so I know every vertex has degree d. It's going to send a flow of 1 over d on every edge that it leaves. Okay? All right, because one flow is coming in, every node has degree d for some fixed number d. If I send 1 over d unit of flow on every edge, the thing that's coming out is 1, right? D times 1 over d is 1. Because every node on this side also has degree d, right? The edges, every edge that's incoming has 1 over d on it, right? They sum up to 1. So that means I can also send one flow out. Okay? All right? So that means I'm sending flow n, right? There's n nodes. I'm saying for every edge connecting the source to one of these nodes, I'm showing you how to send flow 1, right? I do 1, and it splits it evenly to on all of its edges, 1 over d, right? I'm saying every node has d edges coming out of it, or d degree d, right? So they say, OK, one thing is coming in. I'm just going to spread it evenly. And then on the other side, there's only d things coming in, right? That's the assumption I'm making. Well, then 1 over d times d is 1. Okay? And that means I can also put one thing here. So I demonstrated a flow that has value n. Okay? It's not a matching, right? Because the flow has value 1 over d on these edges, right? But I know from the Ford-Fulkerson algorithm that if I give you a graph with integer capacities, the max flow will be guaranteed to be integer. I showed you a flow of value n. The max flow can only be better. It's at least n. So that means Ford-Fulkerson will find a matching of size at least n. Okay? So you see like how we rounded from like a rational solution to an integer solution. That's like pretty cool, right? We're just saying, I just have to demonstrate some mixing, some average of matchings, but that will actually correspond to an actual matching. Okay? So that's pretty cool. And it's like this is a non-trivial theorem to prove. Like if you were proved by induction, it'll take you a while. You have to use this thing called Hall's marriage theorem over and over again. But here it's a consequence of flow, like a trivial consequence of flow. What that means is like, OK, every bipartite graph with degree d on every node actually has d perfect matchings. You can take them one out one at a time. Okay? All right. That's it. So hopefully I convinced you that flow is a very powerful primitive. It's especially useful for problems where we're trying to assign things, and you have some constraints. Yeah, that's it. Thanks.